This is a hex and square collet block set. These blocks are used for holding parts with the aid of a 5C collet. Now, this round part is locked securely in the collet block. And the collet block and part can be clamped in the vise, and features can be produced very easily on 4 different sides. The hex collet block can be used in a similar way for producing features on 6 sides of a part. This is a V-block named for the V's found on 2 or more sides of the block. These V-blocks can be used in several different ways for holding parts. One way to hold a part in a V-block is the clamp like this. You can then take this assembly, insert it in the vise, lock it down, and machine features in the part. For other applications, such as machining features into the end of the part, you can use the V-block in a vise like this. And of course, the V-block can also be down on its side, clamped down, used in this orientation. You will often have large or irregularly shaped parts that don't fit well in a vise. Often a good way of securing them to the milling machine is with hold-down clamps. You can see here we've removed the vise. Now we'll set the part up on parallels. This is to allow us to drill holes through the part without worrying about damaging the bed of the machine. The clamp that I just installed has steps in it that mesh with steps in the other half of the clamp. You adjust the position of the pieces of the hold-down clamp so that this part of the clamp is slightly tilted up in the back, making sure that the contact point between the clamp and the part is at the nose of the clamp. Be very careful here. Tightening these bolts the right amount is one of the most skilled operations in the shop. Tightening them too much and you damage the part or even the bed of the mill. Don't tighten them enough and the part may move when being cut or even be thrown completely off the machine. Most of the time that you're making features on a part such as this, they'll be perpendicular or parallel to one of the surfaces. It makes it very easy to insert this part in a vise and hold it accurately and securely in place. Now, a convenient way to set up a part like this so that you can machine features that are not perpendicular to these surfaces is the set of angle blocks, such as these. Now, this is a right triangle, so you have a 90-degree angle and two 45-degree angles. The other part of the pair has a 60-degree angle and a 30-degree angle. Now, if, for example, I wanted to machine a 45-degree flat on this part, let's start by putting in the 45-degree angle plate, holding the part up firmly against the angle plate, and locking the part in the vise. Can now know that I can machine the part accurately and it will be held securely in the vise. With these two angle plates, you can machine 30-degree angles, 60-degree angles, 45-degree angles. For other angles, use an angle block set such as this. Starting at the biggest angle plate, we have 30 degrees. They come down in increments of 5 degrees, down to a 5-degree angle. From there, in 1-degree increments, down to 1 degree, and a half a degree, and a quarter of a degree. By stacking up the right combination of these plates, you can machine at any angle you desire. Now, what can we do to machine a feature, say, that is at 45 degrees to either of these two faces? Now, if we put the part in place here, you can see that the angle plate is much too large to allow us to clamp the part in the vise. So one way of dealing with this problem is to use a vise in a vise. Now, this is a standard drill press vise. The sides are ground parallel to one another, so we can securely clamp this vise in the larger vise. Now this part is locked securely in place with these surfaces at 45 degrees to the axis of the milling machine. Angle plates and drill press vices can be used to securely hold parts in many positions. They can also be used to conveniently secure parts that would otherwise be very awkward to hold. Say, for example, you wanted to drill a couple of holes in this shelf bracket. Notice this shelf bracket is tapered. We try to lock this in the vise. We can't hold it securely. One way of dealing with this problem is to first lock the shelf bracket or other part firmly in the drill press vise, and then, using the angle block, bring the drill press vise in contact with the other side of the angle block and then lock the vise in place. A lathe chuck can be used for holding parts in a milling machine. What we've done is machined flats on the back of this lathe chuck to allow us to securely lock the chuck in the vise. This is not a highly accurate method of locating a part, but it's very quick and very convenient. Most of the features that you make in a piece of sheet metal like this will be done with a shear that made these straight cuts here, or with tools like drills or punches. But there are times when you'll want to make features, typically something like slots, that you would typically do in a milling machine. To start the setup, put parallels in the vise to support the workpiece up near the top of the jaws. And you can see, as I'm locking this piece down, there's a significant amount of distortion in the part. This is usually going to be unacceptable. There's a real problem here, in that if I just barely lock the vise down to minimize distortion, there's a strong likelihood that the part would just come out of the vise while I'm machining it. Now, there's several ways around this problem. A very simple way to hold parts like this, the features are out near the side, which often they are, is to use double-sided tape. We'll start by cleaning the surface of the vise and cleaning the part. Now we'll apply double-sided tape to the top of the vise. Now, if we're careful to start by aligning the edge of the part with the back jaw of the vise, we'll then have a good square reference or features. Push that into place. And now, this part is securely held, and also it is being held without distortion. So you can now make features in the part and know that the part will be securely held. In fact, see how securely held this part is. If you look closely, it hasn't moved away from the vise jaw. There are many applications where double-sided tape is a very useful way of holding parts down. There are other applications when adhesives such as Loctite are very useful for holding delicate parts. You can glue them securely to a much more robust part and then clamp the robust part in the vise. squaring up a part such as this is relatively straightforward. Begin by locking the part lightly in the vise. Bring the machinist square up against one side. Tap on the part until the edge of the part is aligned with the edge of the square. Lock the part firmly in place and then proceed to machining this surface. No difficulty encountered with machining a part with this sort of aspect ratio. However, when machining a part such as this with a much higher aspect ratio, that is, it's relatively thin compared to its length, you can have some problems. We clamp this part in the vise and take a pass along the surface. Can demonstrate the kind of problems you may have. Along here, this cut was proceeding pretty well. But as we get out towards the end of the part, this cantilevered out of the jaws, you can hear more and more vibration. And you can imagine that that gets worse and worse as the part gets longer and longer. There are a couple of problems with this vibration. One of them is that it produces a poor surface finish. The part vibrating around means that the cutting tool contacts the surface at different points. So you get a rough surface finish here. And another major problem, especially if you're working in a shop with other people, is the noise that this produces. If you're alone dealing with noise that you're producing or you're responsible for, it's reasonable to wear something like headphones for ear protection. If you're working in a larger shop, you really want to hear what's going on around you. It's really a safety consideration. So what we can do to effectively increase the stiffness of this part is simply grab a couple of pieces of stock, such as this. Place these in the vise and simply sandwich the part in between them. Now we have the benefit of the stiffness of these two pieces in addition to the stiffness of the part. And a cut we take now will be much smoother and make much less noise than the cut I just took. As a part like this gets longer and longer, you may find that even stock as heavy as this will not be adequate. In that case, you'll find you can improve the situation considerably by clamping the ends of the stock. Now this does a couple of things. One, clamping here, you couple the stiffnesses of all these parts together somewhat and effectively produce a stiffer beam than you would have by having the ends free. The other thing you do, because this coupling isn't extremely good, it's not as if we bolted them together or welded them together, it allows a very slight amount of motion, and there's some friction and some dissipation associated with that motion. So we get effectively damping out of this. So any oscillation that tends to occur in this plate will be damped out by the sliding effect between this plate and the two plates next to it. I'm taking a cut this time of roughly equal depth to the cut I took before. And you'll hear that there's a very big difference in the noise produced, especially as the cutter gets out towards the end of the part. And also, closer inspection will show that there's a better surface finish as well. Now, this approach can be used even on parts much larger than this. For example, using this approach, it's possible to simply insert a part this large in the vise, insert some large pieces of stock in the front and back of it, and successfully be able to machine the top surface of this part all the way out to the ends. Machining features on the end of long, slender parts presents a certain set of problems unique to this sort of aspect ratio. You can see that if this part were considerably shorter, inserting it in the vise using V-blocks or clamps would be a reasonable way to support the part. However, with this sort of aspect ratio, it's difficult to control the position of the end of the part accurately, and this part will not be very stiff in this position. So machining the surface with a setup like this will produce large deflections in the part, rough surface finishes, and inaccurate features. A way to deal with this sort of part is to clamp it very securely down in the vise and then gain access to the end of the part with the right angle attachment. Now, what this is a very simple right angle gearbox that takes power out of the spindle and runs it through a right angle so that you can install standard Bridgeport R8 taper collets and tool holders in here and then gain access to the end of the part. Some things to note here: there are 3 screws forming this clamp with 2 different functions. The 2 large screws here are for closing the clamp, closing it down around the quill. The other screw has a very different function, and that is to separate the clamp during installation. I want to start by making sure the clamping screws are backed off and loose. And then back off the middle screw until it stops making contact. You'll feel it loosen up quite a bit. Bring it down until it's just snug, and then give it no more than about 1/8 of a turn. Now, what this is doing is spreading this gap here, making this hole a little bit larger so that it will fit over the quill. Being too aggressive about this and giving it even 1/2 a turn risks cracking the right angle head down through here. So this is cast iron and it's relatively brittle. So you want to open this gap up just enough to allow you to install it on the quill. This is a fairly awkward operation because, like all the standard collets and tool holders, this taper has a keyway in it. You have to align the keyway with the pin inside the quill while at the same time wrestling with 20 pounds of cast iron. Okay. Now, see, it's still free to turn. While it is free, you now want to tighten the drawbar. Okay, now that the drawbar is tight, remember to back off the middle screw first. Now it's safe to tighten the clamping screws. Okay, you want to tighten these now until they're just snug because we need to align this head. It's still free to move this way. We do this with a dial indicator. We run the dial indicator along this precision reference surface. We proceed here much like squaring the vise. Bring the indicator into contact at a displacement of about 5/1000ths of an inch. Okay, 15, 20, 25, 30. Just stop it there. Bring this back around until it's close to where we'd set it before we start moving. Start in the center again. Bring this around about 10. Bring this across, see how we're doing. Okay, we're quite a bit closer now. It's off by about 12/1000ths from here to here. That's close enough now so we can snug this down a little bit more. And then with a soft hammer, tap on this until we've rotated it into alignment. See how we're doing. Okay, we're off by about 10. We're off by about 5. Tighten it a little bit more. Okay. Please always use a soft hammer here. You notice where I'm tapping? I'm not responsible for those. But somebody using a hard hammer. You can do this for a few times and get away with it. But in repeated use, doing something like this eventually leaves you with a need to buy a new attachment. You're off by about 10/1000ths across the entire face. And you proceed this way, tapping it and checking it until this surface is square. Now that you have the right angle attachment in place, you can use all the standard tools, such as drill chuck. Install that this way, and drill holes in the ends of long parts. And similarly, if you want to use milling cutters, you can install those in the same way and mill features on the ends of long parts. The part I showed you is actually a small example of the kind of piece you'll often use this technique for. You're making large structures. This is a piece of 3-inch square aluminum stock. It's quite reasonable if you want to machine holes, features on the ends of a part this large. To do so, simply by installing them in the vise, and locking them in place securely. When you're working on a part that's this long, there's a significant risk of not having it quite square in the vise. So it's a very good idea with long parts to check the height of the part relative to the bed of the machine at several points to make sure that the part is in fact parallel to the bed. There are times machining a part like this when you'd like to machine some features down the length of the part and then cut slices through the part to produce many identical pieces. In other applications, you may not want to go all the way through the part, but cut, say, a very deep, narrow slot in it. And an end mill will only let you go so deep for a certain width. You typically have an aspect ratio of 2 or 3 to 1 in terms of length to width. A very long end mill might be as much as 8 to 1. But if you want to cut a slot that has a higher aspect ratio than that, the standard tool for doing that is a slitting saw. And these can have aspect ratios as high as 40 or 50 to 1. Okay, now I've installed the slitting saw. I'll install the part in the vise. Get it squared up. The machine is square. Lock it down securely. Now I've just finished one relatively light pass. That's about 20 thousandths of an inch deep. It's a good idea until you get really familiar with the behavior of slitting saws to make the cuts you need to make like this, relatively shallow, and take several passes if you need to make a deeper slot than that. It's very easy to shatter one of these saws. It's also important to use a considerable amount of coolant or cutting fluid when you're using one of these saws. Unlike wood saws that have considerable set in the teeth, these saws are very nearly flat, so they do tend to bind a little bit unless there's a lot of coolant there. In this particular case, we're using a soluble oil here, which is actually about 90% water. The remaining 10% is a special oil that is emulsified in with the water. What I'm going to do here is take a cut that goes all the way through the part. Now, this part had features milled down the length of it. You could cut off pieces this easily and make many, many duplicates of the same part. Start by installing the right angle head in this configuration and square up the vise relative to the x-axis. Now I'll install the slitting saw in the right angle attachment. And I'll install the part in the vise. Now we're in a position to take a much longer cut down the length of the part, and in addition to that, in this configuration, we can see what's going on both sides of the cutter. So if there is any trouble with any chips binding in the teeth of the cutter, we'll see that in time and be able to stop the machine, save the part and the cutter. Now, I normally try to minimize the use of cutting fluids in order to both see what I'm doing better and also minimize exposure to toxic compounds. And we proceed like this until the cut's finished. I'll stop for a minute here, point out a couple of things. Notice the speed which this is running. This is about 500 RPM. This tool could run much faster than this, especially with the coolant being used to keep the teeth cool. But in this configuration, if the tool does catch in the part and the tool breaks, it's going to shatter and fly towards me and up and away from the machine. So by running at this low speed, if anything really bad does happen and the tool disintegrates, the pieces won't fly very far or do much damage. Considerable care should be used when installing a rotary table. Typical table such as this will weigh around 100 pounds. So if you accidentally slip with this table when you're anywhere near the machine, there's a strong likelihood you'll damage the machine and or the table. So begin placing a piece of wood or other material, sheet of nylon or something like that, suitable as well, on the bed of the machine. Place the rotary table on the bed and flip the table up on its side. You need to do this. You can clean the bottom of the table. Make sure there are no chips adhered to the surface. And also you want to make sure that the bed, the milling machine, is nice and clean. This table is installed with the same T-slot nuts and bolts that are used to hold the vise in place. Now the rotary table is firmly, rigidly attached to the bed of the machine. The next step is to locate the center of the rotary table relative to the center of the spindle. You start to locate the center of the rotary table by installing a drill chuck. In order to hold an indicator like this. Now we bring the indicator down close, not too close. This is a very rough adjustment. Spin the indicator around. You can see where the indicator is going. I need to move the table a little bit this way and back a little bit. Okay, we're pretty close now. So now what we do is adjust the indicator so that we can put it down inside the hole that's in the center of the rotary table. And we want to set the indicator so it's somewhere around half of its full travel. Now, when we rotate the chuck, you can see the dial swinging. What we want to do is keep adjusting the X and Y axes of the machine until we see no motion of the dial. We check it here and swing it around. The other side, check it there. If there's any difference, adjust for that difference in the X-axis, and then do the same thing in the Y. Okay, it's reading the same all the way around now. So we've now located the center of the rotary table relative to the spindle. At this point, you should either set the dials on the hand feeds to 0 or set your digital readout to 0. There's another easier way to perform this operation if you have the right tool. And that tool is called a coax indicator. The coax indicator looks very much like a dial indicator, but with one very important difference. That is, and this is mounted in a chuck or in a collet, the dial is free to turn relative to the spindle position. What this means is we can offset into this indicator, bring it down close, just as we did before the dial indicator, check to see that we're close. This type of indicator has considerable amount of travel, so we only need to get within about 1/8 of an inch or so for this to work well. And now we'll bring it down inside the hole. And set the machine in low range, and then turn the machine on. This is ever so much easier than watching where a dial is going. Just hold the dial steady in front of you, and then adjust the axes. Adjusting a little bit too far, wrong way. The thing to do with this tool is to not watch where the dial is going here, just to watch the ends of travel. So as I turn the y-axis, you can see the travel is growing, so I'm turning it the wrong way. So turn the dial the other way, you can see the travel getting less and less. And as I keep going, it starts to grow again. So I went a little bit past the 0 point. I'll back off a little there. Okay. Okay. It's now very accurately centered. Now that we have the rotary table centered relative to the spindle location, we can attach parts to the table through the use of the same kind of T-slot nuts that are used to hold the vise and hold down clamps onto the bed of the milling machine. This rotary table has several uses. A fairly obvious use is to machine circular parts. Got large parts on here that are too large to fit in the lathes that you happen to have in the shop. You can clamp them down to this surface, and even with a machine the size of this milling machine here, you can actually machine parts that are 3 or even 4 feet in diameter. Now, other applications are, since you have this degree wheel here, and on the handle and the crank, you've got degrees marked out with a vernier that allows you to set the position to within a fraction of a degree. You can put parts on here that you want to make regular features in. Things like bolt circles, slots, grooves. And you can also use this for machining segments out of a part. You can machine pockets in parts, adjust the table, move to another quadrant, another octant. You've got complete flexibility here because you can control the angle down to a few minutes of an arc. This is a standard 5C collet indexer. Holds collets such as this and allows you to hold parts in the collet, lock them down, and through a set of gears that mesh sway, you can position the part in any one of 24 locations. So you have come up to the 6th location, number 4, and there are 3 of those number 4 positions. Stopping the indexer at those positions allows me to produce 4 features of whatever sort. Drilled holes, flats, slots, any sort of feature at all. Now, because there are 24 teeth here, you can produce 2, 3, 4, 6, 12, and 24 features symmetrically spaced about apart. And for example, you may want to attach this piece very securely to some other bracket or piece of shafting or flange. You might want to do that with a bolt circle, say with 6 bolts. So we'll set this to 0, offset the tool to half the bolt circle size, and start drilling. Now, in general, it's a good idea to locate a feature, center drill it, and then do whatever else you plan to on that feature without moving away from that feature. However, this is sufficiently repeatable so that we can move away from here and promptly go past the point we're after. 1, 2, 3, 4. Down center drill again. 1, 2, 3, 4. 1, 2, 3, 4. We're now halfway around. 1, 2, 3, 4. 1, 2, 3, 4. There. Now, in a very short period of time, I've produced 6 very accurately center drilled holes. Now I can remove the center drill, replace it with a tap drill, go back around the circle, drill all those holes, take the drill out, and then proceed to tap all those holes. It's also possible to get other numbers of features with only a little bit more difficulty. What you need to do there, for example, if you want to make, say, 16 features around here, we can't do that with this particular gear that's in the device. What we do then is go around starting at 0, skipping 3 each time, making 8 features, and then offsetting with the X and Y axis the indexer to locate a hole that is symmetrical with respect to the 8 holes you've already put in. Then you proceed around just as before and make 8 more holes that are symmetrical with respect to the first set of 8. Now this is fine for holding parts up to about 1 inch in diameter. But if we take this cover off, remove the part from the collet, have a set of threads here. And these are the threads that you commonly find on a South Bend lathe spindle nose. So, any chuck, faceplate, any other piece of tooling that will fit on a South Bend can also be used on here. This threaded attachment works fine on a South Bend because you're almost always cutting in the direction that tightens the chuck. Here, that may not be the case. Forces produced during drilling may, in fact, tend to loosen up the chuck. So it's important, once the chuck has come down into contact, make sure it's locked firmly in place. Now, with this chuck here, it's possible to machine parts like this. Lock the part in place. Offset it to the desired bolt circle. Reset the indexer to 0, and now you can start making your bolt circle.